2, 3, check 1, 2, 3. Turn down the gain too.
I didn't touch that.
Oh, somebody did. Check 1, 2, 3. Check 1, 2, 3.
Yeah,
Check 1, 2, 3. Right. That's your right level.
Are there batteries around here?
I hope so.
Oh, these batteries. Okay.
I'll leave you to.
Sure. Those are charged right there? Totally.
I added both questions because it's really important that you guys know what they're asking for. Because your expected earnings are going to be different than the casino's expected earnings. So this is a discrete problem, so we can set it up with our x value and then the corresponding probability. Thanks. So our x's for this case So the x's for this case, I don't think this is. Our x's are going to be what you're either winning or losing. So you're paying $2 to play, so you're either going to lose $2, or if you win $7, since you technically already bet 2, you can only win 5. Now, this is set up to calculate your expected earnings. That's why we have the -2 and 5. This is for yours. And then the casinos, they're either going to gain $2 or lose 5. The probabilities stay the same. So if you roll either a 2 or a 4, you win. So at a 2 out of 6 chance, or 1 out of 3, for winning the $5. Now, losing the $2 is either going to be a 4 out of 6 probability or 2/3. Like I said, the probabilities don't change for who's winning and who's losing because the game is still played the same. It's just depending on which aspect you're looking at. So whenever they say expected earnings really is asking you to solve for the mean. So these are both discrete problems. So to solve for the mean, we're just going to take the x value times by its probability, so -2 times 2/3, and add it to the next one. Added to the 5 times its probability of 1/3. Which should give you -33 cents for your expected winnings. And then for the casino, it should give you +33 cents. For the gambling problems, you're expected to lose, so your expected earnings should be negative. Unless it's a game where it's not set up at a casino and you have crazy odds of winning. So then the next one, am I still good with pacing? Are you guys doing okay? Okay. So the set of data is uniformly distributed from 0 to 40. So whenever I think uniform, I think about SpongeBob, because SpongeBob's uniform is a square box, right? So when you have uniform, you're going to draw your box. Your C value goes on the left, and your D value goes on the right. C is always going to be the lower number, and D is going to be the higher number. So we can set this up from 0 to 40. If you guys did not go over uniform distribution, that's fine. Just kind of sit tight through this. So when we have uniform distribution, we're really trying to find the area in the box. So the first thing we need to do is find our height. So our height is going to be equal to 1 over the d minus c. So in this case, our height's going to be 1 over 40, because it's just going to be 1 over 40 minus 0. So then if they want to find the probability that x is greater than 23.5, we can place on here where we think our 23.5 is. And since they want to know greater than that, we're looking on this side of the box. So now this half is kind of irrelevant. You only need to worry about this side now. So we have our height being 140, but we need to find our width. So what we're going to do is just take the 40 and subtract out the 23.5 to give us 16.5 between the two values. So now to find the probability, we can just take the width, so the 16.5, and times it by the height of 140, and that will give you your probability. Now the next one you guys can try on your own, but for the last one where it says the probability that x is equal to 20, for this problem is set up by finding the area inside the box. So if they wanted you to find just the probability that x is equal to 20, if we set that up, that's just a solid line. We have no width to times by the height, so we can't do it. The probability that x is equal to any number in this case is always going to be 0. Okay, so the next one says, it is claimed that a new surgery procedure has a 70% chance of success. Suppose a doctor does the procedure on 4 patients. What is the probability that the procedure works for at least 3 of the 4 patients? So we need to first determine what kind of problem this is. They give us a chance of success, and our probability of x is equal to the number of successes in the trials. So we know that this is going to be a binomial problem. So we need to find the probability that the prescription works for at least 3 of the 4 patients. So we want the probability that x is greater than or equal to 3. So when you're working with binomial, you can either use the chart or the formula. For this problem, we have to use the formula because our n value is 4. The charts only start at n is 5, so we know that we have to use the formula for this. The formula is going to be the combination of the total number times the x that you're looking for, your p-value to the x power, and then your q-value to the n minus x. The formula gives it to you in the probability that x is equal to the x value that you're putting in there. So since we need 3 or 4, we need to use this formula for both 3 and 4, and then add them together. So the first one would be the combination of 4 choosing 3. We have a 70% chance of success to the 3rd power. And then our q value is always going to be 1 minus p. So 0.3, and then 4 minus 3. Then we can add that to the probability of getting 4. So the combination of 4 choosing 4. Again, we still have the same probability of 0.7. Now it's going to be to the 4th power. And our q is going to be to the 4 minus 4. And once we add that up, we can get the answer for this problem. So the next one, at a particular apartment complex, there has been an average of 3 break-ins per month. Find the probability of exactly 1 break-in during that month. So a few things to note about this problem. It's talking about averages, and it's giving it to you in a unit of time or space per month. So we know that this is going to be a Poisson problem. And for Poisson, you also have both the formula and the chart. So if we're looking at the chart, we need to find the probability of exactly one break-in. So the probability that x is equal to 1. If we're working with the chart will give it to you in the probability that x is less than or equal to a number. So if we want it to be exactly 1, we have to take the probability that x is less than or equal to 1 and subtract out the probability that x is less than or equal to 0. If you guys are using the formula for this, the formula works just like the binomial formula, where it will give it to you in x is equal to the number that you plug in for. So if you guys decide to use the formula for this, you can just plug in your x value of 1 and it will give you the answer. Okay, so I'm going to skip down and start with the newer stuff. So it is known that 83% of UCF students would prefer to do their homework in the library versus elsewhere. In a survey of 564 students at UCF, 460 of the students said that they would prefer to do their homework in the library versus doing their homework elsewhere. They want us to test the hypothesis to conclude that the true percentage of UCF students who would prefer to do their homework in the library differs from 0.83. So first, we need to state what our parameter of interest is. For your parameter, you have a few options, but they're always going to be the letter. No numerical values are ever going to be your parameter. For this, we're talking about percentages, and they give us different proportions in the problem. So our parameter is just going to be p. Next, we want to give a point estimate of the data. The point estimate is going to be the numerical value of the p hat, since we are dealing with a proportion problem. So since they said that 460 students would prefer to do their homework in the library out of the 564, that value is going to be your point estimate and is also going to be equal to your p hat. Okay, so now let's test this hypothesis. So we want to test to say that the people who prefer to do their homework in the library differs from 83%. So our null hypothesis is going to be p is equal to 0.83. And our alternative hypothesis is going to be that p does not equal 0.83. Since we are testing that it's not equal to, this is going to be a two-tailed test. And they told us that our alpha value is 0.05. So whenever you have a two-tailed test, you have to take the alpha value and split it in half. So in this tail, we're going to have 0.025, and again with this tail. Next, we need to find our critical value that corresponds to these two values. So because our n value is greater than 30, we know we're going to be using the z-tables. That looks like 36, but it's 30. So if you guys are in Jurassic's class, Ingrid's class, or the honors class, you guys can just look up the 0.025 in your z-tables. If you guys are in the other classes, you would have to look up the value that's in the middle, which is going to be the 0.475. And this gives us our two critical values of negative 1.96 and 1.96. with our rejection regions being the tails. So now we have our rejection region set up with our critical value, and now we have to determine what our test statistic value is to see if we're going to reject the null hypothesis or not. So the formula for finding the test statistic is going to be p hat minus p divided by the square root of p times q over n. So in this case, our p hat value, like we said, was 460 divided by the 564. Our p value is going to come from what we made in our alternative and null hypothesis. So this is going to be the 0.83. Again, our p-value was 0.83, and our q value is just going to be 1 minus the 0.83. Our n value is going to be the total value of 564 students. So we should get something around negative 0.037. So then we can place our test statistic on the chart. So it's going to go somewhere over here. And since it's not in the rejection region, we're going to fail to reject the null hypothesis. So if we fail to reject the null hypothesis, there's going to be insufficient evidence for the alternative. So the next part says find the p-value. So when you're looking for the p-value, it really depends on what kind of tailed test problem you have. We have a two-tailed test problem. So we can go ahead and draw our chart again with the two tails. We have now two test statistics, one of negative 0.037 and one of positive 0.037. The only time when you're going to have two test statistics is if it's a two-tailed test. So once we've placed these on our new charts, the p-values are going to be everything to the right of the positive one and everything to the left of the negative one. And since these are z-scores, you can use your z-charts to look up these values and find your corresponding p-values. Okay, so next we want to describe a type 1 and type 2 error. So again, I'm just going to put our null and alternative hypotheses. So a type 1 error is when you say the alternative is true, but the null is true. So in this case, we would be concluding that p does not equal 0.83 when it does. And then a type 2 error is just going to be the opposite. So saying the null is true, but the alternative is true. So next we want to construct a 95% confidence interval of the true proportion of those who prefer to do their homework in the library, and they want us to interpret the results. So since we're dealing with proportions, the formula for finding the confidence interval is going to be p hat plus or minus z alpha halves times by the square root of p hat q hat over n. So right now we have the p hat, q hat, and the n value. We just need to determine what our z alpha halves is. So since we have 95% confidence, that means that there's going to be 95% confidence in the center of your graph. So we can divide that in half again and get the 0.475. And if you guys are in Sikora's class, Scott's class, and Udin's, you would look up the 0.475. However, if you guys were in the other classes, you would have to look up the 0.025 on the outsides. Another way of determining what the tails are for this is you can take 1 minus the percent confident, so 1 minus the 0.95, get 0.05, and then divide that in half. So again, we'd get a z-score of 1.96, and negative 1.96. So next we can just plug that into our formula. So our p hat, 460 out of the 564, plus or minus 1.96, the square root of 460 over 564, then 1 minus 460 over 564, divided by our n value of 564. Now, something to note about this, if the teacher were to ask for the sampling error is going to be the value you get from doing this side of multiplying and dividing everything together. So once we find the value for this whole entire side, this is going to be the sampling error, because this is what we're adding to the p hat or subtracting from the p hat to make the confidence interval. Okay, so I'm going to skip down to this one at the bottom. A tire company claims that their tires last on average less than 3 years. A random sample of 23 cars was taken, and it was found that their tires lasted an average of 2.8 years with a standard deviation of 0.9 years. They want to test the claim using alpha of 0.01. So for this, since we're dealing with averages, our parameter of interest is going to be mu, and our point estimate is going to be the value of x bar, which was found to be 2.8. So we want to test the claim that the tires last on average less than 3 years. So we're going to have our null hypothesis be that mu is equal to 3, versus the alternative that mu, what do they want? Less than 3. So since we're doing less than 3, this is going to be a left-tailed test. And they gave us an alpha value of 0.01. So we can go ahead and put that in our tail, and now this is going to be our rejection region. In this problem, they said that it was a sample of 23 cars. So our n value is 23. Because our n value is 23 and it's less than 30, we know that this is going to be a t-test. So we have to use the t-tables. When you're using the t-tables, you're always going to look at the tail, t for tail. So when you go to your t-tables, you have to go under the column of 0.01, and you have to look up your degrees of freedom. Your degrees of freedom is going to be your n value minus 1, so in this case it's going to be 22. So you get a value of negative 2.508, which is your critical value. Now we have to find our test statistic to see if it falls in the rejection region. So to find the test statistic for t, we're going to take our x bar value, minus out the mean, divided by the standard deviation, divided again by the square root of our n value. So our x bar value was 2.8, minus out the 3. Our standard deviation was 0.9, and our n value was 23. So that gives us a value of negative 1.066, which does not go in our rejection region. So again, we're going to be failing to reject. So the 90% confidence interval is going to be set up really similar to the last one that we did. Way down there. Except for now, our formula is going to be our x bar value plus or minus the t alpha halves times by the standard deviation divided by the square root of n. And it's important to note that S is going to be the same thing as sigma. So if you see either of those in the formulas, it's going to be the same thing. So our x bar was 2.8. They want a 90% confidence interval. So that means 90 divided in half is going to be 0.45. And 0.05 on the outsides. So since this is a t-tailed test, we have to look up the 0.05, again with our degrees of freedom of 22. And we get 1.717. So now we can add that to our formula. Our standard deviation was 0.9, and our n value is 23. And this would give you the confidence interval. Okay, the next one, the following is a 95% confidence interval for P, 0.34 to 0.68. They want to know how large was the sample used to construct this interval. So we can use the formula n equals z squared pq over se squared, because we're wanting to find how large was the sample. In this formula, you can think of P and Q as either the overall P and Q, or you could also think about it as P hat and Q hat. So since we have a 95% confidence interval, our Z is going to be equal to 1.96. And how we find our P hat in here is we're going to take these two values, add them together, and divide in half. So we get a P hat value of 0.51, which means our Q hat is going to be 0.49. Now to find the sampling error, we can take the 0.68, subtract out the 0.34, and divide that in half to give us the 0.17. So now plugging this all into the formula, we have n equals the 1.96 squared times by 0.51 and 0.49, all divided by 0.17 squared. And we should have gotten around 49. And remember, whenever you're solving for your n value, you always have to round up to the next number. An estimate is needed of the average age of patients in a doctor's office within 0.1 with 95% confidence. The standard deviation is unknown, but it is known that the average ages will range in value between 10 and 75. How many customers should be sampled? So for this problem, again, they're wanting to find the n value, and they're talking about the average age. So you know that we're dealing with a mu problem. So the formula for solving for that is going to be n equals z squared times sigma squared divided by the sampling error squared. However, they don't give you the standard deviation for this one. It says that it's unknown. But they do say that it's known that the average ages will range in value between 10 and 75. So what we can do with this is we can find an estimate of the standard deviation. So this will depend on what your teacher has told you to do. Some teachers want for the standard deviation to be the range divided by 6, and some want the standard deviation to be the range divided by 4. So it just depends on what your teacher has told you to do. So to find that, our range is going to be the 75 minus 10, and then either divide that by 4 or divide that by 6. And using that, then we can plug it back into the formula, and you would put it into the range value. Your sampling error can always be found because it's going to be the one where it says within and then that value. It's important to make sure that if they're saying within a percentage, like a percent, so if they said it's needed that the average age of patients in a doctor's office within 10%, make sure you make that percent into a decimal. Don't put it in your sampling error as 10, put it in as 0.1. And whatever value you get for your n, make sure you round it up to the next number. So then the next one, Angela wants to determine the proportion of UCF students that would prefer chemistry over statistics. How large of a sample is needed in order to be 90% confident that the estimate will not differ from the true value by more than 3%? So now we're dealing with proportions, so it's going to be back up to the formula we used before. So z squared pq divided by our se squared. 90% confident will give you a z-score of 1.645. So we're going to have n equals 1.645 squared. And in this case, they don't tell you what your p and q value are. They just say 90% confidence and that it won't differ from the true value by more than 3%. The not differ from the true value by more than 3%, that's going to be your sampling error, which, like I said, we can't keep it as 3. We're going to have to put it as 0.03. If we don't know what our p and q value is, we're going to use 0.5. And then that's how we'd solve for that one. So the next one, they gave us 2 different sample populations, one with an n value of 53, one with an n value of 51. They gave us the mean and standard deviations, and they want us to use a 90% confidence interval to compare the mean values. So these are going to be 2 large independent tests. So if we want to construct a 90% confidence interval to compare the mean values, we are going to be using the formula x bar 1 minus x bar 2 plus or minus our z alpha halves times by the first standard deviation and that n value, and the second standard deviation divided by its respective n value. Now it's important that when you guys are doing the square root, that you take the standard deviation and divide it by its n value and then do the next one. Don't add the top ones and then divide by the total of the bottom. It'll give you a separate answer. So we want 90% confidence, and both of our n values are greater than 30. So we know that our confidence is going to be with z. 90% confidence, again, we have 90 divided in half, which gives us 0.45. Or you could have done 1 minus the 0.9 to give you 0.10, and then divide that in half to give you the 0.05, which goes on the tails. When we look up these values in the z table, we get the z-score of 1.645. So now we can plug everything into our formula. So our first x bar is going to be 0.035, minus out the second one of 0.340, plus or minus our standard deviation of 1.645, times by the square root. The first standard deviation is going to be 1.046 squared, divided by its n value of 53, and then add it to the standard deviation of 0.96 squared, divided by its n value of 51. And that's going to be how we find the 90% confidence interval to compare the mean values. So if we want to conduct a test of hypothesis at alpha is 0.10 to compare the mean values, they're just wanting to compare the mean values. They don't tell you that they're expecting one to be greater than the other one or one to be less than the other one. They just want you to compare them. So whenever they say that and they don't give you any other information, they want to see if mu1 minus mu2 is equal to 0 or is not equal to 0. So our null hypothesis can be set up mu1 minus mu2 is equal to 0, And our alternative can be mu1 minus mu2 does not equal 0. They told us that our alpha value is 0.10, and we know that since we're doing not equal to, that it's going to be a two-tailed test. When we do a two-tailed test, we have to take the alpha value and divide it in half. So we get 0.05 on each tail. Next, we have to find our critical value. So since both of our n values are greater than 30, this is going to be using a z-score. So depending on what your z-table is, you can either look up the 0.45 or the 0.05 to again get the 1.645 for our critical values. And then the tails are going to be our rejection regions. So next we have to find our test statistic to see if it falls in the rejection region. So for a two large independent tests, our test statistic is going to be equal to the x bar 1 minus x bar 2 divided by the square root of the standard deviation 1 squared over its n value and the second standard deviation over its n value. Now for these tests, if they were going to have you test that it would be equal to something other than 0, let's say that they said conduct a test of hypothesis to see if mu1 minus mu2 is equal to 4. If that's what they were asking for, we would have to subtract out the value of 4 right here in our formula. But since they're just asking you to compare them, we know that we're just dealing with 0, and so we don't have anything over here. So our x bar 1, again, is going to be the 0.035 minus out the 0.34. The first standard deviation, 1.046 squared divided by 53. And add that to the 0.96 squared over 51. So we should get a z-value of around negative 1.69. And now we can place that on our chart. So that is actually going to fall in our rejection region. So we're going to reject the null hypothesis. If we reject the null hypothesis, there's going to be sufficient evidence to support the alternative. So the next one, we have, again, independent samples, except for both of the n's now are less than 30. And it doesn't even matter if both of the n's are less than 30, only one n value out of the two has to be less than 30, and it's going to automatically be a small independent test. So we want to conduct a test of hypothesis for alpha is 0.10 to test that mu1 minus mu2 is equal to 0 against mu1 minus mu2 is not equal to 0. So very similar to the last one, except for this one's going to be set up differently because it's a small test. So again, it's going to be two-tailed. Our alpha is 0.1. So our rejection regions are going to be 0.05. But now, since we're using a t-tailed test, we have to find the t-value that's our critical value. So now, instead of our degrees of freedom just being our n value minus 1, our degrees of freedom is going to be both of the n values added together and then subtracting out 2. So in this case, our degrees of freedom is 42. I know some of the t-charts don't go down to 42. That's fine. We're just going to use the closest one, which is at 40. Usually for the tests, they'll make these numbers a lot lower so that when you're doing it on the test, you can actually find the exact value. So if we go over to 40 and we're using 0.05, we're going to get 1.684 and negative 1.684. So now that we have our critical value with our rejection region, we need to determine our test statistic to see if it falls in there. So since we are doing a too small independent, our test statistic t is going to be equal to x bar 1 minus x bar 2 divided by the square root of sp squared over its n value plus sp squared over the second n value. So sp squared is a specific formula, and it's important to note that once you find the value, don't square it again. The formula is for sp squared. So the formula for solving for that is going to be n1 minus 1 times its standard deviation squared added to the second n value minus 1 times by its standard deviation squared, all over n1 plus n2 minus 2. So for our case, our first n1 value is going to be 20 minus 1 times by the first standard deviation, 1.99 squared. Add that to n2, 24 minus 1 times by its standard deviation, 2.13 squared. All over both of our n values, 20 plus 24 minus 2. So we should get around 4.3. So now we can go back and plug that into our formula. So our x value 1, x bar 1 is going to be 3.7 minus 3.3 divided by the square root of 4.3 over 20 plus 4.3 over 24. So we should get a t-value of around 0.64. So then we can place that on our graph. So 0.64 is not going to fall in the rejection region, so we can fail to reject the null hypothesis. So then the next one, a paired difference experiment yielded the following: an ND of 30, an X bar D of 10.5, and an SD of 4. And we want to test that the mu D is equal to 0 against the mu D is less than 0 using alpha of 0.10. So one way to tell the difference, this one specifically said paired difference, but if it did not say paired difference is taking the same sample and running 2 different tests on it. That's why you only have one ND value, and you're just taking the difference between the 2 experiments that they ran. Whereas for all of the independent samples, there's 2 specific different samples. Even if your N value is the same, for this one our N1's 20 or N2 is 20, even if they have the same N values, this is 2 different samples, 2 different groups of 20 people or 20 things. Whereas for paired difference, it's going to be one sample, and that same sample is going to do 2 different experiments. So we want to test that mu D is equal to 0 against mu D is less than 0. So this is going to be a left-tailed test. Our alpha value of 0.10 can just go in the tail without having to be divided, and this is going to become our rejection region. Since our ND is equal to 30, we're going to be using the z-charts. So depending on which class you're in, you can either look up the 0.10 or the 0.4 to obtain your z-score. And we should get a value of negative 1.28. So now we have our critical value corresponding to our rejection region, and now we have to see if our test statistic is going to fall in this range. So for a paired difference, to find your test statistic, you're going to do T is equal to your X bar D. And then again, if we were subtracting, or if we were finding anything other than 0, we would have to subtract it out right here. Divided by your SD, and then divided by the square root of your ND. So for this, our XD is going to be equal to 10.5. Our standard deviation is 4. And our ND is going to be 30. Oops. For this, we have to also subtract out the mean value that we're testing for. So our mean value again is 0. So for this, we get a value of 14. That's going to be way high. It's high because I made up the problem. So if you guys on the test, is probably not going to be that large of a value. But for this case, 14 is going to be somewhere off the chart. So we're going to fail to reject. Now, if we wanted to do a confidence interval for this, the confidence interval formula for this is going to be X bar D plus or minus T, alpha halves, times by your SD divided by the square root of ND. Let's say we are doing a 94% confidence interval. So again, 94 is going to be divided in half. And we get 0.47. and 0.47. And then you would get the 0.03 over here. You would look up this value to get your t-score, and then you would plug it all into this formula. So that's kind of the basis of how you guys do the Chapter 9 problems. Since we have some extra time, we can go back and do some of the ones from the beginning problems that we didn't have time to do. So let's go back and do some of the ones for where the z is the standard normal, and we need to find our z0 value because that seems to give students a lot of trouble. So there are a few basic setups for when you're solving for your z0, and I'm just going to go ahead and kind of write out the different options you would have. So if they're giving you the probability that z is less than z0, and your probability is less than 0.5, when you set this up, your z0 value is going to be over here. It's going to be negative, and you're going to place whatever probability they give you right here in here to solve for your z0 value. If they were giving you the probability that z is less than z0 and your probability is greater than 0.5, since it's greater than 0.5, we still know that the greater than 0.5 is going to go on the left, but we have to start on the right side now. We have to cross over the midline so that everything to the left is going to be whatever value they gave you of the greater than 0.5. So in this case, this is where your z0 would be. And then this is where you would stick your probability. If they were giving you the probability that z is greater than z0 and it's less than 0.5, we're going to be dealing with the right side of the test now, and we're going to place our probability over here in the tail with our z0 right there. If they were doing the probability that z is greater than z0 and they give you a probability that's greater than 0.5, again, anytime it's greater than 0.5, we can't just put it into one of the little tails. It has to cross over the midline. So now our z0 is going to be on the left-hand side. It's actually going to be negative now, and the probability that they give you is going to go on the right. If they want the probability of negative z0 to z0, you're going to set it up your midline with the negative z0 to the left and the positive z0 to the right. Then, to find this, in here in each one of these, this is going to be your probability that they gave you divided in half. If they gave you a problem that said -2 something like that, where this is a 2, not a z, you'd set it up, place your midline. -2 is going to go on the left. And now, depending on what this probability is, depends on where you're going to place your z-score. Because -2, once you look that up in your z charts, you're going to get a value of 0.4772. So if this probability is greater than 0.4772, we know that our z-score is going to go over here. And whatever is left from the probability after we subtract out the 0.4772 is going to be placed right there. And then kind of the last option that's seen is when they go from 0 to z naught. In that case, 0 always goes right down the middle, and our z naught's going to go somewhere on the right-hand side, and whatever probability that they gave us is going to be placed in here. Same if they did from negative z naught to 0. It would just be the opposite. So we'd have our 0, and then our negative z naught's going to be here. And then whatever probability they gave us, we would place in here. Now, all of these problems can be set up the same for if they're talking about x and x naught. The only difference that you would do between the z's and the x naughts is you're going to have to take your x values and use the mean and standard deviation that they gave you to find the z-score and then work with it. So if they gave you a problem where your x bar was 30, your standard deviation was 10, and they said the probability of x being less than x naught is 0.10, we can set it up just how I set them up for the z-scores. So we would place our x naught over here with a 0.10 right here. And then what we would do is, depending on which class you're in, you would either look up the 0.4 or the 0.10 to get a z-score of negative 1.28. And it's going to be negative because it's on the left. So then once we get our z-score, we can then convert it into an x value. So we have the negative 1.28. We can say x bar is also equal to mu. We don't know our x. Our mean value is going to be 30 over our standard deviation of 10. And then we would just times the 10 by the negative 1.28, add the 30, and get our x value. So you can do all of these the same way. You just have to make sure that the first thing you're doing is taking your z-score and converting it into an x value. Everything else is set up the exact same way. It's just one extra step. So we have some time for questions if you guys want to ask any questions or go over anything. Yeah. Sure. So she wants to go back through the first page real quick. And while she's looking at the first page, we can also just talk about what these would be. So how would we find the mean? So we would just add up all of these values and divide by the amount of values. To find the median then, we would just find the middle number. So you can kind of put them in order and then just one by one walk your fingers down. And in this case, we have 2. So since we have 2 numbers in the middle, we would just take the 17 plus the 18 and divide it in half. The mode is going to be the one that happens the most, so that's going to be 16. The range is going to be the highest number minus the lowest, so 56 minus 10. The variance and standard deviation you guys can solve for in your calculator. And then that's kind of what we went over. So if this one was set up the opposite way, if it was a skewed right test and we had the same 3 parts, the mode is still going to be the one where it's the highest. And then since it's skewed right, the mean is going to be greater than the median. and we're still going to place them in the same. So it's still going to be mean. Median and mean. Does anyone else have any questions they want to go over? Yep. Finding the p-value? Sure. So when we're asked to find the p-value, it's going to depend on what kind of tailed test we're working with. So you find the p-value is based off of your test statistic. So the first part of finding the p-value is finding your test statistic with the given formulas. Now the next part is going to be based off of what kind of tailed test you have. So if your alternative is solving for less than, whatever value you get for your p-value, whether it be over here, whatever value you get for your test statistic. So let's say your test statistic is over here, or your test statistic is over here. No matter what kind of value you get, since you're solving for less than, your p-value is going to be everything to the left. And you would look that up depending on which chart you're using, whether you would use the z or the t. If your alternative hypothesis is testing for something greater than, usually your test statistic will be somewhere on the right, but not always. So even if it's way over here on the left, your p-value is going to be everything to the right. Then if you're testing the alternative hypothesis being not equal to, we draw our two tails. For this one's kind of, I guess, easier in terms of where to put the test statistic, because for the not equal to, you're going to have two test statistics. You're only going to get one from the formula, but you're going to take the positive and the negative value of these test statistics. So you're going to have one over here and one over here. And then your p-value is going to be everything to the right of the positive one and everything to the left of the negative one. Now, finding the p-value is going to be easier if you're looking it up in the z-charts, because you can just look up that exact score or find whatever's closest. However, if you guys are wanting to find the p-value for a t-tailed test, you guys are going to have to look up the range of the p-value. So let's say we are doing some sort of t-tailed test where our n value was 10. So in this case, our degrees of freedom would be 9. Let's say we got a test statistic of 1.5. To find the p-value for a t-tailed test, you have to first look at your degrees of freedom. So if we were to have a degrees of freedom of 9 on the charts, you would go to where your degrees of freedom is 9. So degrees of freedom is 9. My tables are a little off because can I borrow yours real quick? Your t-table. Thanks. Okay. So here's our t-table. Sorry if it's a little hard to see. So if we're in a degrees of freedom of 9, we have to find in here where 1.5 would fit in. It's super important that you don't try to find 1.5 throughout the whole thing. You are only looking at your degrees of freedom. So since our t-value is 1.5, in the degrees of freedom of 9, 1.5 would fall somewhere between 1.383 and 1.833. It would be somewhere in between these. So since it's somewhere in between these, we're going to go up and write down what the t-value range was. In this case, for 1.383, the t-value was 0.10. And for 1.833, our t-value was 0.05. Thanks. So what this means then is for the t-test, we can't find an exact p-value unless your teacher has shown you guys how to do that on your calculators. If not, then they'll just ask for a range. Your range for the p-value for one of the tails would be 0.05 to 0.10. If this was a two-tailed test, however, you would have to take this range and multiply it by 2. So instead of the range being 0.05 to 0.10, if this was a two-tailed test, this would then become 0.1 to 0.2. Did that kind of help? So if you guys look on your T-tailed test, way at the bottom, there's going to be a row that's labeled infinity. So the infinity column on your T-test table, or your T-charts, that's going to be used. You can use this for when your n value is greater than 30. So let's say that they gave you 95% confidence interval. We know that we can do the shorthand version of 1 minus 0.95 to get 0.05, divide that in half to get 0.025. If our n value is greater than 30, we can go to our T-chart, go to infinity, and just look up this 0.025, and it will give you the z-table value of 1.96. So if you're looking to use the infinity, it's only when your n is greater than 30, and it's important to note that the value that you look up for infinity is going to be what's in the tail. So if we had the 0.475 here and the 0.025 here, when you're looking on the infinity, it's going to give you this 0.025. So that's what we'd be looking up. You would never try to find the 0.475. Did that help? Do we have any other questions? Yep. What do you mean? Okay, so for finding the NCR on your guys' calculator, I'll show you guys once on this one and then once on the other kind. So if you guys have this kind of calculator for doing the combinations, you can either write combinations as NCR, you could do NR, and then C, NX. Either way, they're all the same thing. So what you're going to do first is type in your greater value. So let's think that we were doing 50 choosing 5. We would first type in the 50. We go to math, over to probability, down to NCR, and hit 5. And that would give you your combinations. So when you guys are using the binomial formula, and the first thing is NXC with N and X for your combinations, that's going to be the first aspect of it. Now, if you guys have the other calculator, you guys are going to type in the bigger number first again, so 50. And then above the 8, you can see it says NCR. That's going to be combinations. So you do second 8, and then you would type in the second value of 5. And then real quick to find the standard deviation in your guys' calculators. So if we were using, let's say we were working with these numbers, 5, 4, 3, 2, and 1. If you're using this calculator, it's important to go off first and then on. And you're just going to type in the number 5 and then press E+. Then 4, E+, 3, E+, 2, E+, 1, E+. After you've done that, next you're going to go second and the square root button. This will give you your standard deviation. So from this standard deviation, then you can find the variance because you would just square it. So for this kind of calculator, again, every time you have to do it, you're going to have to go off and then back on so the number is clear. You just type in the number, hit E+, next number E+, next number E+, next number E+, next number E+. Then second square root, and you'll get your standard deviation. Wow, sorry guys. For this kind of calculator, to solve for the standard deviation, you're going to go to Stat, Edit, To get rid of the values, if you guys notice, if you hit clear here, none of them are going to go anywhere. You have to go up to where it says L1, hit clear, and then go down and they'll go away. Then you can just type in the values, so 5, 4, 3, 2, 1. After you have them all typed in, you go back to Stat, over to Calc, hit Enter, Enter, and that's going to be your information. Your X bar is going to be your mean, your N is going to be just your sample size, and your SX is going to be the standard deviation. I know it might be tempting to pick the sigma. Don't pick the sigma. It's not the right answer. So the standard deviation on this kind of calculator is going to be the 1.58. And then again from that, if you wanted to find the variance, you would just take this value and square it. Does anyone need me to repeat that? The variance? The variance, you would just take the standard deviation. So if you had this calculator, you would just take this number. This one, 1.58, same thing. You would just take it and get the square of it. So 1.58 squared is going to be equal to the variance. If you're using this calculator, all you have to do is just press x squared, and that will give you the variance. This one, you have to go back and type it out and then hit x squared. For Poisson. So, like, what do you mean? Because the Poisson has the formula and the charts. Did you want to just go over? Okay. So, where was the Poisson one? Okay, for this one, for Poisson, you can either look at it in the chart, or you can use the formula. Do you know what the formula is for the Poisson? What is it? Okay. Over factorial? Okay. So she was saying mu for these. For Poisson, you can also say lambda because it's going to be the same thing. So if you wanted to do this in your calculator, for the first one, let's say that our mean was equal to 3. So we could do 3. If our x was 1, then e to the negative 3. So you're going to go 3. Yx is going to be your exponent. So you're going to go 3 to the 1 times by e to the negative 3. Negative 3 you're going to put in first and then do second ln. And then to get the factorial down on this calculator, you're going to divide by, if we had an x of 1 factorial, we're just going to do 1, and then the factorial is going to be the second e button, so second 3. And then that's how we would get the answer. Did that help? So whenever you guys are doing the e, it's important that you guys put in the exponent first and then do the second ln. And then if you wanted to do e on this kind of calculator, your e is going to be the second divide by sign. And then to put it to the exponent, you guys are just going to click this one up here that has the little hat and type in whatever exponent you want. Yeah, so in this kind of calculator, yes, you would type in your exponent first and then do second ln. And remember that the formula is going to give it to you in x is equal to a number, and the chart's going to give it to you in less than or equal to a number. Thanks. And before you guys head out, can you make sure that you guys fill out the evaluations and leave them on here? Any other last minute questions? 45. Yeah, so in the evaluations, in the little bubbles, will you guys bubble in 45? At the top, it has like the little bubbles. So good luck on your guys' exam, and if you guys have any other questions, you can come up and see me. But otherwise, good luck on the exams. And thank you for coming. Oh yeah, and I have this formula sheet up here if you guys want to come look at it. Yeah, and all the z's, like the z naughts, you guys can come up here and take a picture of it too. Where did I put that?